Next, we're going to look at ways of comparing lines in three-dimensional space. And so there are three possibilities that come up. Okay? So they will intersect if they have a point in common, they're parallel if their direction vectors are parallel. And I guess we should specify that they don't intersect, because otherwise they're the same line. So we'll assume that these are two different lines, okay? Although that is a possibility. And there's a third possibility that we don't have in 2 dimensions. Either lines are parallel or they intersect, and those are the only two possible scenarios. But in 3 dimensions, there is a third possibility. Lines could be skew if they are not parallel and they don't intersect. Okay? And the reason that this can happen, right, in 3 dimensions but not in 2 is that those two lines, they can live in parallel planes. So we might have, say, one plane there and another plane there, right? Oops. And one of the lines is, say, going in that direction in one plane, and the other line is going in a different direction in the other plane, right? And so they will never meet because they're in parallel planes that have no points in common. But they are not parallel because they are going in different directions. So that is a third possibility that you can encounter in 3 dimensions. Okay, so we've got an example here, and I think we'll use the example to talk about, well, how do you actually figure this out? How do you determine which scenario you're in? In particular, how do you find that point in common if the two lines intersect? Okay, well, let's come over here and let's look at the direction vectors for the two lines. Okay, so L1 has direction vector, let's call it V1. And we can just read off these numbers, right? If you think about comparing the vector form of a line, the equation of a line, to these parametric equations for a line, right? The coefficients of the parameter t tell you the direction vector. So the direction vector in this case is 3 minus 1 and then 1, right? L2 has direction vector V2, and now we have 4, 1, and 2. Okay, and those two vectors, they are not parallel, right? Because to be parallel, one would have to be a scalar multiple of the other. In particular, we see that 1 has to get doubled to get to 2, right? But this one is not 2 times minus 1, right? So they're not scalar multiples. So they can't be parallel. So we've ruled out the possibility that they could be parallel. So now we move on to intersection. We look for a point of intersection. So what would be a point of intersection? It would be some set of values, x, y, and z, that work for both sets of equations at the same time. Now, one of the things you'll notice that we're using t for one of the lines, we're using s for the other. Some books and some people will make the distinction between an intersection and a collision, right? And so the idea is, if you could actually solve both equations with the same parameter value, like so t on one side and t on the other side, and there's some number you can plug in for t over here and the same number for s there, and it gives you the same point in both cases. You might refer to that as a collision. Whereas a point of intersection is you could get the same point for about one value of t on this side and a different value for s on the other side. And the collision comes from, I think, one way to think of it, there are a number of ways you can sort of think of this, but imagine, let's say, you think about projectiles or airplanes, but maybe you'd rather think about projectiles because we don't like to think about airplanes colliding. Think about two projectiles could pass through, we could have one projectile passes through a point, and then sometime later, another projectile passes through the same point, right? And so if there are lines that describe the paths of those projectiles, they both pass through the same point, so the lines have a point in common, they intersect, right? But they pass through at different times, so the two particles never actually meet, or airplanes if you want to think about it that way, right? Whereas if they pass through the same point at the same time, then they collide. Now, a collision is much less likely because then you have to, we have sort of three, we can think about this as sort of, it's going to be three equations because we're going to equate the x's, we're going to equate the y's, we're going to equate the z's. We get three equations. Three equations with two unknowns might still be unsolvable, but it's more likely to have a solution than if we have three equations with just one unknown, okay? And so the way we go about solving this is for an intersection, we would need to have 1 plus 3t equal to minus 2 plus 4s, equating the x's. We would need to have 2 minus t equal to 3 plus s, if we equate the y's, and then we would need t to equal to 5 plus 2s. Okay, so what we do is we clean these up, we try to get them into sort of a more standard form, so we might write it like this. 4s minus 3t equals 3, okay? This one, s plus t equals, if I move the 3 over, minus 1. Here, s minus t equals, if I move the 5 over, minus 5. Right? So we get these three equations. 1, 2, 3. And now we play around with those. And so if we do, for example, it's easier to work with 2 and 3. So if we do 2 plus 3, if we add those two equations together, we're going to get the t's cancel. So we get 2s equals minus 6. So s is equal to minus 3. And now from there we can take that value for s and plug it into, let's say, 2. Or, notice you could also subtract those equations if we subtract them. That works too. But let's just plug in the 3. So putting that value in 2, we get that minus 3 plus t is equal to minus 1. And so that tells me that t has to equal 2, right? And so the catch here is that any two of those three equations are probably going to tell us the values of s and t, unless maybe one of the equations is somehow redundant. But this solution has to also work in the first equation. So here is where we decide whether we are dealing with an intersection or skew lines. We go now to the equation 1, and we say, okay, so we have 4 times s, which is negative 3, minus 3 times t, which we found to be 2. And so that's minus 12 minus 6, that's minus 18. Well, that is not equal to 3, okay? And so we cannot find a common solution for all 3 variables. So there's no solution. Oops, that's a U. Solution. And that means that the lines are skew. They're skew lines, right? If we had found a set of values s and t that worked for all 3 equations, they would intersect. But because we can't find a set that works for all 3 simultaneously, the lines are skew.